Uniform motion. A constant steady speed or motion is called uniform motion. On a graph, it appears as a straight line going neither up nor down. Everything in the universe moves. It might only be a small amount and very slow, but movement does happen. Don't forget that even if you are standing still, the Earth is moving around the Sun and the Sun is moving around our galaxy. The movement never stops. The term that describes motion is mechanics. Over the years, scientists have discovered several rules or laws that explain all motion you might find. There are also special laws when you reach the speed of light or when physicists look at atoms. The physics of motion is all about forces. Forces need to act upon an object to get it moving. Motion won't just happen on its own. How is all of this motion measured? Physicists use some basic terms when they look at motion. Speed, velocity, acceleration are few. Velocity is a value for the basic speed of an object. Speed is achieved after the action of a force. Velocity is just another word for speed. It is the rate of motion in a specific direction. For example, I am going that way at 30 km per hour. My velocity is 30 km per hour. It is also described as a measure of distance divided by time. Velocity can be constant or it can change. Acceleration is a twist on the idea of velocity. Acceleration is a measure of how much the velocity of an object changes. When velocity is changing, the word acceleration is used. Velocities could either increase or decrease over time. Mass is another big idea in motion. Mass is the amount of something there in grams or kilograms. A car has a greater mass than a baseball. There are two main ideas when you study mechanics. The first idea is that there are simple movements, such as if you are moving in a straight line or if two objects are moving towards each other. There is a special thing called instantaneous velocity, that is the velocity at a split second in time. The term instantaneous refers to something physicists call a limit. Scientists limit the amount of time they do the measurement. When the limit moves to zero, that limit is one tiny point in time. We measure your velocity as the limit for a period to time, 0, to get the instantaneous velocity. Just as the velocity, there is something called instantaneous acceleration, the acceleration for specific moment of time. Newton's physics describe about 90% of the way things work in the universe. His ideas start to break down when you talk about ideas such as objects moving at the speed of light, the inside of atoms, extreme temperatures, and when the objects are huge, like galaxies interacting with each other. Rest and motion. Rest and motion are relative terms. A person sitting in a moving car is at rest with respect to his or her fellow passengers, but is in motion with respect to other objects or people on the road. It is not possible to define absolute rest or absolute motion. Absolute rest is the complete absence of motion, which is not possible to visualize because all the objects in the universe, electrons in an atom, molecules in solids or gases, solar systems in galaxies, etc., are in motion. By the same logic, it is not possible to visualize absolute motion. To define absolute motion, the motion must be described with reference to a point which is absolutely at rest or absolutely fixed in space. Such a reference point does not exist, hence it is not possible to define or imagine absolute motion. Concept of a point object. A cricket ball may be spinning while it is moving as a whole in a trajectory. Also, a body may vibrate as it moves. For example, a falling water droplet. These complications can be avoided by considering the motion of a very small body called a particle or a point object. Motion is a state which indicates changes of position. Surprisingly, everything in this world is constantly moving and nothing is stationary. The apparent state of rest, as we shall learn, is a notional experience confined to a particular system of reference. A building, for example, is at rest in Earth's reference, but it's a moving body for other moving systems like train, motor, airplane, moon, sun, etc. Motion. Motion of a body refers to the change in its position with respect to time in a given frame of reference. A frame of reference is a mechanism to describe space from the perspective of an observer. In our daily life, we recognize motion of an object with respect to ourselves and other stationary objects. It would be surprising for some to know that we live on this earth in a so-called stationary state without ever being aware that we are moving around the sun at a very high speed, at a speed faster than the fastest airplane that the mankind has developed. The earth is moving around the sun 100 times greater than the aircraft's speed. The simplified motion shall refer motion that involves one-dimensional, rectilinear and uniform motion. In uniform motion, speed is constant. This means that a graph of the motion must also be constant, that is, a straight line. Thus, uniform motion can be defined as motion moving in a straight line at a constant speed. The straight line going neither up nor down. Absolute motion. We have to change our mindset about perceiving motion and its scientific meaning. To our trained mind, it is difficult to accept that a stationary building or tree standing at a place for the last 50 years is actually moving for an observer who is moving towards it. Going by definition of motion, the position of the building or tree in the coordinate system of an approaching observer is changing with time. Actually, the building or tree is moving for all moving bodies. What is required is that the study of motion requires a new scientific approach about perceiving motion. Mathematically, a particle is treated as a point, an object without extension, so that rotational and vibrational motions are not involved. There is no such a thing in nature as an object without extension. The concept of a particle or a point object is very useful because real objects often behave to a great extent like particles. A body need not be small in the usual sense of the word, in order to be treated as a particle. For example, if we consider the distance from the Earth to the Sun, with regard to the distance between them, both the Earth and the Sun can be treated as particles or point objects. We can find out a great deal about the motion of the Sun, planets and other celestial bodies without appreciable error by treating these bodies as particles. Moreover, any object can be treated as a point object if it covers distance which are much greater in comparison to its size. A cricket ball moving in a field and a train covering hundreds of kilometers are some examples. Distance and displacement. Distance and displacement are two quantities which may seem to mean the same thing, yet they have distantly different meanings and definitions. Distance is a scalar quantity which refers to how much ground an object has covered during its motion. Displacement is a vector quantity which refers to how far out of place an object is. It is the object's change in position. For example, consider the motion depicted in the diagram. A boy walks 4 meters east from A, then 2 meters south, followed by 4 meters west, and finally 2 meters north and reaches A. Here the boy walked a total of 12 meters. His displacement is only 0 meters. During the course of his motion, he has covered 12 meters of ground. That means a distance equal to 12 meters. When he finished walking, he is not out of place. There is no displacement for his motion. Displacement in this case is equal to 0 meters. Displacement being a vector quantity must give attention to direction. The 4 meters east is cancelled by the 4 meters west, and the 2 meters south is cancelled by the 2 meters north. Speed and velocity. Just as distance and displacement have distinctly different meanings, so do speed and velocity. Speed is a scalar quantity. It refers to how fast an object is moving. A fast-moving object has a high speed, while a slow-moving object has low speed. An object with no movement at all has a 0 speed. But velocity is a vector quantity which refers to the rate at which an object changes its position. Imagine a person moving rapidly one step forward and one step back, always returning to the original starting position. This might result in a frenzy of activity. It would also result in a zero velocity. Because the person always returns to the original position, the motion would never result in a change in position. Velocity is direction aware. Average speed, velocity. As an object moves, it often undergoes changes in speed. For example, during an average trip to school by car or by an auto, there are many changes in the speed. The speedometer of the vehicle may cross 50 km per hour at some time. At some times, it may be 10 to 20 km per hour. But during the course of the trip to school, the average speed might be, say for example, 25 km per hour. Now look at the equations. Average speed is equal to the distance traveled, which is divided by the time taken for travel. And the average velocity is equal to the total displacement by the time taken. Example: Joseph traveled a total of 440 kilometers during the vacation period. He spent a total of 10 hours for this journey. What is his average speed? Average speed equals distance divided by time. In this case, it is equivalent to 440 kilometers divided by 10 hours, which is equal to 44 kilometers per hour. Motion in 1, 2 and 3 dimensions. A body is said to be in motion if its position changes with regard to its surroundings. In order to describe the motions of such objects completely, we need to specify its position. For this, we need to know the position coordinates. In some cases, 3 position coordinates are required. In some cases, 2 or 1 coordinate is required. Based on this, motion can be classified as follows: one-dimensional motion, two-dimensional motion, and three-dimensional motion. One-dimensional motion. It is known as rectilinear or linear motion. A particle moving along a straight line is said to undergo one-dimensional motion. In such a case, only one of the 3 rectangular coordinates changes with time. For example, if we consider one-dimensional motion along the x-axis, then when the particle moves from A to B as shown in the figure, the x-coordinate changes from x1 to x2. The straight line along which one-dimensional motion takes place may be taken either along the x, y or z axis. Examples of one-dimensional motion are as follows: the motion of a train along a straight line, an object like a ball falling freely vertically under gravity, the vertical up and down oscillations of an object from a vertical spring. Two-dimensional motion. A particle moving along a curved path in a plane has two-dimensional motion. The figure given here illustrates a two-dimensional motion where a particle moves from P to Q along a curved path. If the motion of an object is restricted to a plane, it is said to be in two-dimensional motion. Examples of two-dimensional motion are as follows. An insect crawling on a ball. A satellite revolving around the Earth. A projectile motion. A bob oscillating along a curved path. Three-dimensional motion. An object moving in space is said to be in three-dimensional motion. A butterfly flying in air or motion of gas molecules in space are examples of three-dimensional motion. Graphs. Graphs are often the best way to convey descriptions of real-world events in a compact form. Graphs of motion come in several types depending on which of the kinematic quantities like time, displacement, velocity, acceleration are assigned to which axis. Position time graph. This graph helps to describe motion. Consider a car moving with a constant rightward plus 10 meters per second. If the position time data for such a car were graphed, the resulting graph will be like this. Here, note that a motion with constant positive velocity results in a line of constant and positive slope when plotted as a position time graph. Note also the changes in the graph plotted for the two types of motion like this. If the velocity is constant, then the slope is constant, that is a straight line. If the velocity is changing, then the slope is changing, that is a curved line. The position time graph reveals useful information about the velocity of the object. It is often said, as the slope goes, so goes the velocity. Velocity time graph. The most important thing to remember about velocity time graph, that is VT graph, is that they are VT graph and not displacement time graph. There is something about a line graph that makes people think they are looking at the path of an object. A common mistake is to look at the graph given here and think that V is equal to 9 meters per second line corresponds to an object that is higher than the other objects. This is not true. Do not look at these graphs and think of them as a picture of a moving object. Instead, think of them as the record of an object's velocity. In these graphs, higher means faster and not farther. The V is equal to 9 meters per second line is higher because that object is moving faster than the others. These particular graphs are all horizontal. The initial velocity of each object is the same as the final velocity is the same as every velocity in between. The velocity of each of these objects is constant during this 10-second interval. When the curve on a velocity time graph is straight but not horizontal, the velocity is changing. The three curves here each has a different slope. The graph with the steepest slope experiences the fastest change in velocity. That object has the greatest acceleration. Since each of these graphs has its intercept at the origin, each of these objects was initially at rest. The initial velocity being 0 does not mean that the initial position must also be 0. Uniform motion graphical representation. A motion diagram for uniform motion has equally spaced dots along a line, indicating that the velocity has constant direction and magnitude, and acceleration is 0 as shown in the figure. Taking the time between each dot to be 1 second, we get the following graph. Note that the points of all are along a straight line. This is the signature of constant velocity. Since this is a graph of uniform motion, we know that the displacement delta x between each point is the same. Combining this with equal time steps delta t, we can say mathematically that the slope of the line delta x by delta t is constant and is the velocity in the x direction Vx. This is shown in the figure below. The sign of the displacement tells you the direction.